Okay, so we're on our last leg. We're on our last leg of probably studying for this stuff. We're on our last leg because all of these assignments and Blackboard stuff and tests and labs are running all in together, maybe. We're on our last leg of the lecture module because there's very few videos and topics that we need to talk about at this point. And here's an example problem. This example problem says, use curved arrows to show the movement of electrons in each of the following reactions. Hint, look at the starting material and then look at the products and then draw the arrows. That's the stuff that we've been doing. Why is that a hint? All right, so if we look at A, I see the arrow. I'm going to draw a line here. There we go. And I need to compare left to right. What has happened? What's happened? You tell me. What's happened? What do you see different? Well, it looks like this did have an OH, and now it just has an O. In addition, it has a negative charge now. I have to show that hydrogen goes somewhere, right? Where does it go? Does it just end up by itself? No, it doesn't. It looks like that H has left, and it looks like that H has went in to the OH to make HOH, which is water. So these are the steps that I'm going to have to show. Curvy arrow. I start with my negative piece. Here's a negative piece. What happens here? Well, that probably sweet talks hydrogen, and it says, hey, come on, be in a relationship with me. I got what you need. Just end it with that oxygen. I'm a better oxygen. And the hydrogen says, oh, okay. And off it goes. Well, these electrons have to go somewhere. Hydrogen does not want those electrons. All right? So where do those electrons go? Those electrons are between the O and the H right now. And look, this has a negative piece. Well, that's because the oxygen's electronegative anyway, and it would prefer to take those electrons, and that's what it does. So there's the curvy arrow mechanism that represents the formation of the products in part A. That's all I got to do. I show the OH is attracted to the hydrogen. That's how it makes water. Those electrons that are between the O and the H at this point, they have to go somewhere. Where do they go? They go to the oxygen, and that's what makes it negative. All right, so let's look for part B. What do we do in part B? Well, part B, the difference here is that it looks like bromine is attached to the ring, and this double bond has been destroyed. So that's what I have to show. I have to show that bromine is going to go onto this molecule. All right, so how do I do that? Well, I start with the negative piece. That negative piece is not my bromine. There's a positive on it. So the negative piece starts at my double bond. This double bond is going to be attracted to the bromine. And folks, that's all I have to do. That double bond will break. I don't need to show that. This arrow is going to represent it. So that double bond is going to break, and bromine goes on one of those carbons. In this diagram, they've drawn it up to the top. And then the other carbon that was involved in that double bond is going to be shortchanged. And that's why that one turns out to be positive. There's nothing else right now to go into that position. So we leave it drawn as a carbocation. And that's it. That's all we do. All right, so for part C, here we go. There's my arrow. I compare left and right. What has happened? Well, it looks like everything stayed the same here except for that oxygen up on top. This did not have a hydrogen, and now it does. Where did that hydrogen come from? Well, this was H3O, and right now it's H2O. So one of these hydrogens is what did it. My double bond is on the left. My double bond is still on the right. There's no difference there. So what do I need to show here? Well, I need to show the curvy arrow that takes one of these hydrogens and slaps it up on top of that oxygen. Well, I start the curvy arrow at a negative side, and that's with the O. That's where my electrons are. That's the nucleophile. And I point it to one of those hydrogens. Now that hydrogen is going to go, okay, and then it goes off. And it forms this OH up here, and that oxygen realizes that it makes a mistake now because it's positive, it's not neutral anymore, so it regrets that mistake that it did. I hope that you don't regret your life decisions, but this oxygen just did. All right? And then here, we've got some electrons between the O and the H, and we have to show where those go. Well, where do they go? That oxygen's positive. These electrons are negative, so those electrons will go to that oxygen, and that creates a neutral water molecule, H2O. That positive has just been neutralized out by the negatives that were in that bond. There's our curvy arrow mechanisms. That's what the question wants me to show. All right, so for part D, well, what's the difference here? It looks like the only thing that we've done is we've put chlorine onto this molecule. That's it. That's all that we've done. However, curvy arrows start at my negative piece. So I'm going to start my curvy arrow here because that's my negative, that's my nucleophile, and I'll point it to the positive piece because that is the electrophile of the reaction. So my nucleophile reacts with the electrophile. Therefore, I draw the arrow in that direction. It's very important that I draw it in that direction. And that is what ends me up with the product that I see on the right-hand side of this equation. Okay, so there's your intro to chemical reactions. Now, this is not it. All right, there's going to be more to this. There's going to be more to the story, as you can imagine. There's more details that we can bring in. There's more things that we can talk about and everything else. But we're not going to do that in this lecture module. We're going to do that in the next lecture module instead. Something else that I want to talk to you about is in the mechanism, sometimes we refer to a reaction coordinate diagram. This is something that I'll briefly mention, but it's nothing that I will hound on constantly over and over and over. And the reason for this is because we rarely ever use it, to be honest with you. It's something that it's good to look at. It's something that we can pull out of general chemistry and apply it to organic just to kind of reconfirm what you did learn in Gen Chem was important, okay? That's really why we do it. But it's nothing that I just constantly ask about. You might see 1 or 2 questions on it in Blackboard. You might see maybe 1 or 2 questions on the test, and that's about it. But it's going to focus on other material instead. So in the reaction coordinate diagrams, there's always a template that we do, and that template is that on the left-hand side, we're going to have reactants, and on the right-hand side, we're going to have products. And there's a statement that we like. It's really bold at the very bottom, that says the more stable the species is, the compound, the lower the energy is going to be. So this is something that we have to keep in mind. This is a driving force for reactions. So if I've got something over here and I'm reacting something over here with it, and I'm expecting some products that get formed, these products better have lower energy, because if they had high energy, they're going to react again. Okay? I don't want that. I'm going to take these reagents, I'm going to react them, I'm going to get products, and those products better have lower energy, because if they do not, they are not stable, and they are not yet done. If the products do have lower energy than my starting reagents, then there's a good chance that my reaction will go forward as planned without a problem, without an issue, without too much effort on my end, and the products are very happy. Another term that we use in the reaction diagrams are things called transition states. So as we go through the mechanism, and we now know what that means, the nucleophiles and the electrophiles reacting together to form products, we get these middle steps, don't we? We saw some of those middle steps. We drew them out. We kind of had this midway piece with carbocations and stuff. Well, as it goes through the process of the reaction, we can get something called a transition state, and that is the maximum energy state. Again, you'll see this in a diagram that I'll draw in just a second, but this saves me a little bit of time. It saves me some handwriting that you can't read, so at least you can see this on your screen. Transition states, they have similar characteristics to reagents. They also have similar characteristics to products as well, though, because transition means in the change of, right? I mean, transitioning from one period of your life to another means that you're changing. So reactants change into products, and the transition state represents that midway line, right? It's not quite reagents. It's not quite yet product. It's somewhere in the middle, and it's really a blend of both of these together. What this basically boils down to is a diagram that looks like this. You probably saw these in general chemistry when you took that class. We can apply them to organic as well. Over here to the left-hand side, this represents the reactants. And over here on the left-hand side or right-hand side, this will represent the products. So in order for me to go from here to here, a lot of times I have to go up a hill. And this hill sometimes is really steep. And this hill sometimes is very low. But I've got to put some effort in it. This effort comes from a little bit of work. You got to work to get up the hill. Jack and Jill carrying a pail of water. Same thing happens here. These reactants are carrying a pail of water up the hill. You got to put in some work, Jack. You got to put in some work, Jill. Nobody's going to give it to you for free. So if they make it to the top of the hill, and they've put in the effort, and they've put in the work, that top is going to be called the transition state. They are getting ready to look over the hill and say, whew, all that work is behind me. And at this point in time, it is all coast all the way down to the products. But you got to get above that curve first. Well, that takes some energy. For us in a laboratory environment, that energy that is needed could come from something as simple as heat. Heat from a heating mantle. Heat from a hot plate. Heat from an outside source, maybe a reagent that generates the heat internally. That could also come from what we call a catalyst, which will actually lower the hill down. That is the purpose of the catalyst. So that heat that I have to put into the system, I don't have to put in as much. So the catalyst lowers the bump. And the amount of energy that's needed to go from down here, right, here's kind of the flat line, all the way to the top, this is called activation energy, E sub A. These reactions have a certain amount of activation energy in order for them to go forward. And that could come from something as simple as heat, or something that I can contribute to that bowling flask or to that beaker that I have my organic reagents in. Once I give and supply this reaction enough energy, Jack and Jill go up the hill, and then when they get to the top, that is the transition state. They are getting ready to transition from what was before to what is over the hump. And after that point, notice it's all downhill in this example. So it's smooth sailing all the way to the product side at that point. But if I don't give it enough activation energy, if I don't give it enough, what's going to happen is it's going to go back down to the bottom. You did a good try. Kind of like those pinball machines when you were little, right? You had that plunger over to the right-hand side and you pulled that plunger back. If you didn't pull it back far enough, if you didn't slap that pinball with enough energy, what happened? Well, the pinball would go up, but then it would come right back down. It would never go into the rest of the pinball machine. So you would have to pull back the plunger one more time and then snap it real fast. And then that would be enough energy for that ball to leave the plunger and go and start hitting everything else in the pinball machine. That's what we're doing here. We want to make sure we have enough activation energy. You did not have enough activation energy when you pulled that plunger back. Well, here we hope to provide these reactions with enough activation energy. And that's why in a reaction, in a laboratory, it might say heat for 30 minutes, heat for 60 minutes, heat to a certain temperature, because that is ensuring that we go over the hump. And that ensures that Jack and Jill goes over the hill to the product side. It's the only way that works, and that's why we do that. All right? So reagents to the left, products to the right, transition states on the top. Here's another example. I start off with reactants. Up, 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 up the hill we go. And then notice we have a dip. Well, this is going to be a transition state for me. And this could be a first step of the reaction, right? So I'm not really going to be talking about the right-hand side of this yet. We've not really flatlined at this point, but this is going to be titled as a transition state. Well, this is kind of the middle piece. It's kind of a valley, right? The reaction's not quite done yet. This would be very similar to that mechanism step where we created a carbocation. That's what you're seeing here. So that was my double bond getting broken. The hydrogen goes on. I formed a carbocation that took the bromine in eventually. Well, this is that middle step. I'm not quite done to products. We're just kind of hanging out. We're in the transition of. So up at the top is my transition state. That is the first step of the reaction. And then I could take this. That bromine's going to come in. It might not take enough energy or as much, right? That hump could be very, 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 very tiny. But I still have another transition state that could happen here. That's okay. No one says you only have one transition. You can have 2, 3, 4, whatever. And once it goes past that hill, Jack and Jill then go on down. And they go to the product side. Another thing I want you to think about when you look at these activation energy diagrams, is the proper name that we give these, is the version to the left and to the right. Here in this example, my reactants are here, and my products are down here. So what this means is that I have to put energy into it. Heat, 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 maybe until Jack and Jill at the top of the hill. Then after that point, it's all fair game, smooth sailing all the way down. Jack and Jill go whee all the way to the bottom. Notice the product side is lower than the reactant side. So that product side gives me a release of energy, and that's what that represents. That's Gibbs. A negative change of Gibbs is releasing energy. That means that this stuff could be exothermic. Now, they use the term exergonic down here. Exergonic and exothermic. Exothermic means it releases energy in form of heat. Exergonic just means it releases energy. It doesn't have to be in the term of heat. It can be in another form or another fashion, but it releases, it gives off. So this is an example of an exothermic reaction. That's how most of you study that in general chemistry. Exothermic reaction. It gives off heat, and this is why that it happens. However, we could be in laboratory. We could look at some of these organic reactions. We have reactants over here to the left, and we pump heat into it, and Jack and Jill get up to the top of the hill, and then they eventually do go whee all the way down, but it's not a steep decline. And what we end up with here are products that are higher up than our reactants. So that means it required energy from us. The products on the very end, those products are a little bit higher energy. It took some of the energy that we provided it and it kept it. It did not give it back out. And this is what we call endergonic or, in other words, endothermic. So, for example, this reaction I do, it feels hot. And this reaction I do, it feels cold. It absorbs heat from the outside. That's endothermic. All right? So endothermic and exothermic can be determined by the position of the products in relationship to the reactants. If the products are lower, it's exothermic. If the products are higher, then it's endothermic. On these reaction diagrams, we also talked about a valley, didn't we? And that valley also has a term and a name that we can provide it, and that is called an intermediate. So I have a transition state that's here. I have a transition state that is there. And this is an intermediate between the two. That's why we call it intermediate. It's in between two transition states. So an example type of problem that you would see, what is all this going to boil down to? That's what you really want to know, isn't it? So what this is going to boil down to is something that looks like this. So this problem says, which step in the reaction has the greatest free energy of activation? Is the first formed intermediate more apt to revert or to go on to form products? And which step in the reaction is the rate determining step? All right, so I'm going to do more than this. First, I need you to realize that over here, these are reactants. This is where it starts. And then here are products. This is where it ends up. How many transition states do we have? Hopefully you would look at this diagram and say 3. 3 transition states. There's a transition here, there's a transition there, and there's a transition here. So 3 transitions. That's probably going to be a common problem that you might see on a test or in Blackboard and so forth. It's not addressed here, but that's how we determine that. Another question is, how many intermediate stages do we have? Well, intermediate stages are the valley. That represents B. That also represents C. So there's 2 intermediates that could form from this reaction. This basically means that there's multiple steps for these reactants to turn into the products. That's what all of this is about, right? We have the first initial step that happens in the mechanism, and then something forms temporarily. And then we have another change that happens in the reaction, and then something else changes temporarily on the structure. And then we have another change that begins to happen, and then it finally forms product. This is how we regard this energy of activation diagram. So A says, which step in the reaction diagrammed below has the greatest free energy of activation? Well, is it from A to B? Is it from B to C? Or is it from C to D? Greatest energy of activation. What does that mean? That means how high is the hump? Is A all the way to B, does that have a higher climb than B to C? Yes, it does. Does A to B have a steeper climb than C to D? And the answer is yes, it does. So the greatest free energy of activation is the steepest part of the curve, and that is AB. This is going to be the steepest climb. Right there. Is the first formed intermediate more apt to revert or to go on to form products? Okay, well, once it does that, womp, there it goes. So the question that this one wants, the first formed intermediate at B, does it prefer to go backward and go to A, or does it prefer to go forward and go to C? How would I determine this? Well, take a look. Path of least resistance. If I put energy into the system and it climbs up the hill, it can climb up the hill in 2 different ways, can it? It can go up, 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 up this way, or it can go up, 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 up that way. which one would be less work? It looks to me like it would be less work to go left-handed. It looks to me like if I was going to make B do work and it had to climb up a hill, it would prefer to climb up this hill because it's not as steep. And then if it does, it goes back to reactance. So it could revert and go back to reactance a little bit more. And then see which step is the rate determining step. The rate determining step, this would be your highest amount of energy that's going to be required. After that point, it's all smooth sailing to products. Past that point, where is it going to be? All right, well, if I take a look at A and I go up, 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 and go to B, well, there's still more steep hills to climb, isn't there? If I go to B and I go up, 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 and I go to C, well, there's still a hill to climb, but it's not the steepest one anymore. The hard work is now over. The hard work happened when I bypassed this area here. That area right there. Once I got past that peak, everything else is going to be less work. And I am ensuring at this point that I do get products when I pass that. And that is the rate determining step. Once I get past that one, this steep hill right here, the tallest one, I ensure that I am going to get product after that moment in time. So the rate determining step here is going to be between B and C. When I go between B and C and I get past that hill, everything else, smooth sailing. I might have other hills to climb, but they're not going to be as difficult as the one that I just crossed. Okay, so that is where this lecture module is going to stop. So, we've done another ride, haven't we? We've talked about alkenes, we've talked about shapes and structures and geometry and naming and a little bit of reaction that will happen later on down the road in the next lecture module. We've also incorporated a little thing that we call activation energy diagrams, and this was somewhat of a review of general chemistry. This is stuff that was talked about back in 151 and 152. So all of this is starting to wrap up, again, in a nice little, sweet little package that we call organic chemistry. And this is another reason that people have trouble with it, because it does take some of the old school ideas and topics, and it brings them back, and it just assumes that you know these. But I don't assume. I don't assume anything. And this is hopefully why that you will have a better experience in this class compared to some of the others. All right, so that's where this lecture video is going to stop. Good luck. I hope that you've had good luck on all the assignments. Good luck on the upcoming tests that will focus on this lecture material. And as always, if you have questions, you know how to get a hold of me. And I'll be here. I'll be waiting. Bye-bye.